So as Anthony said, I'm working at Ford now at the AI Advancement Center. I've been here for about 3.5 years. Um, when you think of automotive companies and AI, probably the first thing that jumps to people's mind is self-driving cars, and that's certainly an important application being developed. But there are really many applications of machine learning and artificial intelligence used throughout Ford, and even applications of computer vision. So we'll see if you guys are curious about those. We could also chat about those near the end. But today I'd like to talk about computer vision, which is a subset of artificial intelligence, and give you a little bit of a history. And it's not meant to be a comprehensive or unbiased history, but a little bit of history for how the techniques that are being used today to help computers see were developed. Can everyone hear me okay? Okay. Should I, oh, I do see a head shaking there. Should I turn up my volume? Is this any better? Okay. So what do we mean by computer vision? Let's see. Oh, sorry, there's a slight delay. Hopefully it won't get annoying. Okay, so here's at least a few different examples of vision tasks that we could try to give to a computer. So perhaps the most basic is just an object classification. So look at that picture on the top left, and you want your computer to be able to tell you that that's a picture of a cat in a way that a human would recognize it. In the same vein, the picture below it is slightly more nuanced, but it's an object detection and also localization problem. So you want to not only say that there's a car or several cars in that picture, but provide some information as to where the car is, where the person, where the bike, and so on is. In the lower right, a related task is a scene segmentation. So the goal there is to give kind of a pixel-wise explanation of which pixels are cars, which are the road, which are the background, which are people. Obviously, you can imagine why, if you're trying to teach a car to drive, this would be useful to be able to do. And one which maybe stretches the definition of the term, but is fun to look at anyway, in the top right. This is an example of a style transfer problem, where the goal is to take two images as input and then create one as output that has the content of the first image, but in the style of the second image. So you see this computer generated third image here is this picture of buildings and houses, but in the style of this Starry Night painting. There, as I mentioned, are a lot of applications, even within Ford, just beyond trying to teach cars to see and react to environments. But beyond that, there's some, so for example, in the assembling and inspecting of vehicle manufacturing, there's times where it would be useful to be able to see, either see things quickly or see things, oh, sorry, I apologize, my slides are not advancing the way I want them to. Let me see if I can. Okay, so there's this, there's a vehicle being manufactured there. Computer vision is also being adopted pretty widely in medical imaging and diagnosis, looking at either 2D or maybe 3D scans. And of course, if you have an iPhone, you have this facial recognition technology on your phone, and that's actually probably used by a whole bunch of apps on your phone to recognize and tag and manipulate people's faces. So these are kind of some widespread applications of computer vision. So for a little bit of history, really going back to the 50s, people knew enough about computers and maybe just enough about how the human brain worked to be tantalized to try to build a computer that could learn and think like a human. And so one of the basic building blocks there was thought to be, well, we had this basic understanding of how neurons work in a brain and seem to transmit information. And if we could, program a computer to learn in the same way by taking input stimuli with some network of neurons and producing some output, and being able to update those connections, that could be a step towards or a way towards building artificial intelligence. So here's one of the first attempts at what a mathematical or computer model for that would look like. This is from 1959. So you should read this diagram as the x1, x2, xn on the left. Those are the external stimuli coming into this network of neurons. And you know, the nodes and edges are meant to be suggestive of the structure of neurons and their connections in the brain. So these stimuli get some value, and they have a weight associated with their connection to this secondary neuron. And so the information is fed from the x's, you know, via the weights to this secondary neuron. And basically, if it gets enough cumulative information or cumulative signal sent to it, it'll fire a 1, and if not, it'll not fire. It'll be a 0. So you get some input here with a binary output, 1 or 0, depending on whether you had enough signal coming to this neuron to excite it. So what Frank Rosenblatt did was basically said, if you wanted to learn how to do a simple task, like maybe just replicate some basic logic functions, you could do so with this model. And he described how you could basically take input-output pairs of this function you're ultimately trying to learn, and you know, see if the function guesses wrong on some of the outputs, and there's a way to adjust these weights until it guesses right. And so there's, at least in some simple examples, you could show just explicitly how you would go through this process of learning to get, and so yeah, learning in this case means find the right weights so that inputs will give you the expected output. In this case, just a binary output. So this idea really generated a lot of excitement, but eventually into the 60s, that got tempered down a little bit. So it turns out, well, obviously our brains are much more complex than the picture you see here. And even for some not so complex sounding functions, it's not hard to show. You need at least multiple layers of these neurons stacked together to be able to replicate the complete input to output mapping. And so, you know, theoretically, there's nothing harder about that, but this procedure that was given for learning the correct weights could not easily be applied to networks that had multiple levels of neurons like this. And that's basically because you put in an input, you get an output, but if that output is wrong, instead of trying to say which of these weights we should change, you have this kind of mess of interconnected weights. So that really, at least for the time being, into the 60s, was kind of the extent to which computer scientists thought about having networks of neurons do learning inside of a computer. But another important advance at the time, although not, I mean, so this was not done by computer scientists, not with the aim of teaching computers to think, but by just cognitive physiologists, Hubel and Wiesel. They were trying to understand specifically vision, how a cat's brain takes visual input stimuli and processes them. So they hooked up some electrodes to a cat's brain, and they would show the cat different pictures and try to see by the electric activity, you know, what was going on inside that cat's brain. And they basically failed to do what they wanted to do with that experiment. But they did notice serendipitously that, so they had these images on slides on a projector, and when they would switch from one slide to the next, they'd notice this neuron firing, and they noticed that this was a repeated occurrence. And eventually they were able to determine by experimenting that what was happening was basically the edge of the slide created this dark, sharp edge shadow, and that was what was stimulating this particular neuron in the cat's visual cortex. And they took this a little bit further and basically came up with this model for how the cat's brain was processing images. Is at first it had these simple neurons that would really just be responding to things like edges with a particular orientation, and they would fire when they saw one of those edges. And that information was then fed to more complex neurons that would aggregate some of this information and presumably put together some more complicated structures. And another important observation made there is that these simple neurons that were doing things like detecting sharp edges, they had small receptive fields, meaning that one individual neuron would only fire when it saw an edge in a particular part of your field of vision, or at least in the case of this cat. So again, these weren't computer scientists. They had no aims of building artificial intelligence, but they did at least suggest if you wanted to model the process of vision as this transmission of information through a network of neurons, this is one way that cats seem to be doing that, and I mean, now we know humans too. But like I said, in terms of actual artificial intelligence, computer vision developing, there wasn't much done after the mid-60s for a while. But one place where there was significant progress in the 60s was with image processing. So a variety of digital images were being created by the 60s, from satellite images to medical scans to this picture here is actually one of the first ever digitally scanned photographs. It was one of the computer scientists had a baby, and you can see, I forget the kid's name now, but kind of a famous. And you can see that the quality wasn't great compared to what we're used to now, and there was a need with these images being created digitally to do some further processing, just to be able to basically see them. So what do I mean by image processing? Here I'm talking about taking an image and processing it with a local filter. So let's just stick with grayscale images. So values, each pixel has a single number value from 0 to 255, going black to white. And so here's an example of a 5x5 grayscale image alongside a 3x3 filter. And so what it means to process this image using this filter is to create a new image, and we'll do that one pixel at a time. So how do I determine the value of this highlighted pixel in the new image? First, I wait till my machine, there we go. Okay, so here's this gold pixel here in the new image. How do we determine that value? Well, you find the corresponding pixel in the old image, and you overlay this filter on top of it. And then you just take the weighted sum of these pixel values with the weights coming from the filter. So in this case, I would be taking 8 times that center value minus the surrounding values. And that turns out in this case, if my math was right, to be 149. So that's the value of that pixel in this new processed image. And you can do the same for every pixel. You have to decide what to do when this 3x3 box spills over the edge, but there's different conventions you could take there. Not important for our case. So the result is, you take this original image, you slide this filter centered over each pixel, and just taking this linear combination of the nearby pixels, you get some new value. I should have said at the beginning, so on Zoom calls in particular, it's kind of hard to read the audience. So please don't hesitate to interrupt me, ask a question if something is not been explained clearly or not given sufficient treatment, and I'll try to address that. Here, are there any questions about, I guess, just what is meant by image processing with a filter? Is this idea clear enough? So let's look at a couple examples. So here is an image of a car winning a race. Oh, and it looks like that's a Ford GT. Oh, congratulations. So this is a grayscale image here, and let's look at what we get when we process it with this filter. Does anyone want to guess, at least qualitatively, what this processed image will look like with that filter?
It will be darker.
Darker, so it'll certainly be darker. And one way to show that is to observe that these weights add up to 0. And that means in particular, if you put this filter on a uniform patch of the image, it'll return 0, which is black. So a lot of, for example, the racetrack you'd expect to be almost entirely black. And it looks probably darker in general because you're taking some weighted average, basically, of these values. And so a lot of the image will be black. Which parts won't be black? Well, if you have a bigger value in that center pixel than the average surrounding value, that's when you'll get some non-zero return from this filter. So in particular, if you have a white or close to white pixel surrounded by black or close to black pixels, you'll get high intensity return from this filter. And so this effectively is an outline filter. So the process image looks like this. You can see it's, more specifically, it's outlining all the white next to black parts of the image. Okay, here's a second filter. Anyone have any intuition, any guesses what this image will look like?
I'm guessing a blur.
Okay, so it looks like there's some kind of smoothing going on. One thing to notice in contrast to the last one is that, so here the numbers add up to 1. And that means this time if you apply this to a uniform patch of the image, it leaves it unchanged. So let's expect the racetrack, for instance, to still look like a racetrack in the processed image. Now actually there is a separate defined blur filter in Photoshop, for instance. And the name given to this one, well, I guess one more thing we could try to use to understand this is, so okay, the uniform parts aren't going to be changed. What about the non-uniform parts? Well, if the center pixel is whiter than its neighbors, that difference is going to be amplified because you have 5 times that value minus basically 4 times these neighboring values. So this will be like a good laundry detergent. It'll make your whites whiter and it'll make the darks darker for the same reason. So this really, if you open up Photoshop, this is a sharpening filter. So it kind of, and hopefully that this is coming through clearly enough that you can actually tell the difference between these two. But hopefully the second image should look sharper. So it's kind of magnifying the contrast between these white and black areas. Okay, one more filter for this image. So okay, now again, I'll say these numbers add up to 0. So we expect that a lot of this image is going to be blacked out. But what parts of the image do you expect to not be blacked out or to be highlighted by this filter? Any guesses? Well, so this filter is going to return particularly high values when you have higher numbers on the left than you do on the right. So the kind of extreme case here would be if you have white pixels on the left and black pixels on the right, then you're going to get a white pixel returned here. And yeah, so maybe I should have, I don't know if this is overly technical, but of course, yeah, I said these values range from 0 to 255. And of course, that's not guaranteed when you take linear combinations. So let's just say if something is below 0, let's just cap that at 0 and cap it above at 255. So we're not going to go whiter than white or blacker than black. But this filter here effectively is detecting vertical edges in the image where you have white, specifically white on the left of black edges. So if you notice, like on the rear spoiler of the car, of course, there's a front and a back edge there, but this one's only picking up that back edge because that's where the white is on the left and the dark is on the right. Okay, so other than being kind of fun to look at these pictures, the observation to make here is that neurons inside that cat's brain were doing things like detecting edges inside of images or inside of that visual field. And so the observation to make here is that you can use these filters that people have been using for image processing to effectively do the same thing, detect where are there edges, vertical edges in this case, in this image. So really the first person to kind of put those ideas together is fast forwarding all the way to 1980 now. And a computer scientist, Fukushima, built this, what he called a neocognitron network. So it was a similar idea to this neural network that Rosenblatt had built a couple decades earlier, but he specifically wanted to use this for vision, and so he kind of assumed that the neurons in this network should behave like the neurons in the cat's brain. So in particular, you should have some neurons that are simple cells that only look at small portions of the image and are trying to detect simple things like edges. And then whatever output you get from those simple cells should be fed into and combined somehow by these more complex cells. Maybe one thing that's worth mentioning. So if you remember that neural network that I showed you on the first slide, you had a weight, an edge connecting each input to that secondary neuron. And each input in the case of an image is like basically each pixel. So if you wanted to take an image as input into a neural network and do some of this type of processing, you could really quickly start to build up just way too many of those edges, way too many of those weights for it to be feasible to compute. So one of the advantages, other than being kind of biologically inspired by cat vision, one of the advantages here is that these filters that do things like detect edges can be reused basically. So you can look at each individual piece of the image and try to detect edges by using a single filter as opposed to trying to learn unique weights for every pixel. So this is kind of a nice theoretical advance, but in 1980 there was just no one understood how to train something like this. So this never really, at least in 1980, never really was practical. Well, the idea seemed nice. There was no good way to determine what those parameters should be. Maybe let's say a little bit about why that is, what the difficulty is. So what you want to do, once you have this model of what your neural network should look like, you want it to be a function that'll take input to output on whatever your expected training data is. And what you control, or what can be learned, are the different weights between neurons. So really there's a function that says, if you choose weights, then here's the error you'll get by building a neural network with those weights and predicting input to output response. So the real goal in the learning process here is to find the optimal weights you could choose for your network. Once you've already chosen what you want this model to look like, find the optimal weights, and optimal means that they'll minimize some error or loss function that you define. And the sticking point here was, so probably when most of you hear that you want to do an optimization problem, calculus should jump into your mind, and you should say, well, I want to like take gradients of a function and use those gradients to tell me how to minimize it. And what was stifling progress there is this, I don't know if you can see my mouse, but this this binary basically transition output function for this neuron firing. Because if you want to take gradients with respect to these input weights, well, the chain rule here is going to kind of kill all those gradients because its derivative of this function is 0 everywhere it's defined. So there's no good way to figure out, there's no nice differentiable function as a function of these weights. So you can't use calculus basically to try to find what the ideal weights should be. So one way to get around that is to just take a smooth version of that sharp transition function. And the one that got used is this sigmoid function here on the right. So it kind of has the same asymptotic behavior, but it smoothly goes through through 0 here rather than this sharp jump discontinuity. So what that means is that now you can pick weights. Once you pick weights, you can feed your input to the network and get the corresponding output. Then you can compare that output to what you wanted the output to be and see if there's any difference. If there is, you can say, well, how would that output prediction have changed if I change these weights? And basically you can compute gradients, and this tells you how to adjust your weights to get a better prediction. And in practice, it's kind of important that you're able to do this efficiently. So the way this is done for neural networks in practice is that you send data forward through the network, you compute some error, and then you compute gradients, and you do this gradient updating backwards through the network. And so this process is called backpropagation of errors. And it really wasn't, in some sense, all it does is uses the chain rule, but it really wasn't until the mid-'80s that people were able to use this effectively to train neural networks with more than a single layer of neurons. Any questions to this point? Okay, so again, if you replace this sharp cutoff function with something smooth, then now you're able to use gradients to adjust your weights. So now what you can do is take a neural network and just initialize it with random weights, and then take all of your nice input-output pairs, feed them through one at a time, and update those weights, and hope it'll converge on a good model. And really the first success here in the case of computer vision was in 1989 by Jan LeCun. So he's still, I think he's currently the head of AI at Facebook, and he's still very much active in the AI community. And the task that he managed to solve quite well with computer vision was this recognition of handwritten digits. So one of the big applications at the time was, sorting mail by zip codes is a tedious thing to do by hand. If you could have a machine read the zip code and sort the mail by zip code for you, that saves a lot of people hours of mail sorting. But you can imagine it would be hard to explicitly write a program to take an image of a handwritten digit and say, how can we tell when it's a 0, a 1, a 2, or so on? There's plenty of variety and sloppiness in handwriting. And so LeCun here used a convolutional neural network. So it's a neural network whose neurons kind of act like these cat neurons in some sense, using local filters. And he trained it to classify a handwritten digit from a 28 by 28 input. And he was able to do this, using this backpropagation technique for updating weights. So the basic idea, there was kind of a phase one was this kind of local filter recognizing, with a small receptive field, recognizing these local structures. And then there was some kind of pooling or downsampling done to get a smaller image. And so, here's kind of a simple example of, you have a 4x4 image, you can divide it into 2x2 patches, and find some way of representing each patch, either by taking the maximum value in each patch or maybe the average in each patch. And this basically gives you some, lower resolution version of that same image. And so here's kind of a schematic of what this network looked like. So you have this original image, and the first layer of this network took 5x5 filters. And so you can think of this stack of blue squares here. Each one of these is basically a processed image, each processed using its own filter. Then you do this, he did max pooling, so some kind of downsampling of the photos to get smaller 12 by 12 pictures, and then repeated this. So again, you use these filters to get further processed images, downsampled again to get further processed images. These are now just 4 by 4. And at that point, that's only 16 pixels for each of these processed images. These are just flattened into a single vector of values and then fed into a kind of regular looking artificial neural network. And this whole process was trained using labeled images and this gradient updating. Any questions at this point? So maybe it's worth saying, so post offices, at least some of them at this time, they did use computers to help read zip codes. And it wasn't all that different from the picture you're seeing here, except that they were hand chosen filters. So the difference here is that the computer was able to learn through a bunch of examples which of these filters are particularly useful for recognizing handwritten digits. And it was able to outperform the kind of hand-engineered features. So,
I have a quick question.
Yeah.
What would the advantages of using each of the different pooling methods be, like max versus average? Would a max pooling extract the higher level features better or in some way? What are the advantages to each?
Yeah, so I don't, so maybe at least one difference, depending on what types of images you're trying to understand. So this average pooling has an effect of blurring the image, basically. And the max pooling has an effect of, well, it's also kind of blurring, but it's keeping some of the sharper contrast parts of the image. So I think maybe for grayscale images, you lose less features to blurring through this max pooling. But in general, I don't know if there's a good reason to prefer one over the other, but it may depend on what type of features you're hoping to capture in those images.
Okay, thank you.
So this was great. He was able to train a neural network with more than one layer using this backpropagation. But people quickly discovered there was still a problem when you wanted to go beyond more than a couple layers. So if you wanted to do something that was really like a human brain that had a very complex network of neurons, and you'd imagine you'd at least have to have several of these layers stacked together. And an issue there was this sigmoid function that gave us derivatives, which kind of saved the day before. You'll notice the derivative of that function is often really close to 0. And when you take several layers stacked on top of each other and you want to compute derivatives, you get a product of a bunch of derivatives, basically, because of the chain rule. And so it's easy for the gradients to just kind of decay towards 0. And once the gradients go to 0, the model is basically not updating itself. It's kind of freezing in this state of potentially not very well learned. And there's also an issue, though it's not obvious from looking at this function here, but there's an issue of the other thing that could happen is these gradients can explode towards infinity, and then you just get completely unstable learning processes. So this really for another more than a decade, again, stopped progress in getting deeper neural networks, being able to do vision or even other modeling tasks. And another relatively simple idea kind of saved the day here, and that was just, well, let's replace this function with another one where the derivatives aren't going to all decay towards 0. So what eventually became commonly used as this neuron activation function. So we're now getting to the point where it's not as biologically inspired anymore of this 0-1 neuron firing. But if the input to the neuron is negative, it outputs nothing. And if it's positive, it just passes through that positive output basically with the identity function. So now all the derivatives of this function are 0 or 1. And so if you multiply a bunch of ones together, there's no issue of things getting too big or too small. So this, again, pretty simple idea was really enough to open up the gate to training some deeper networks. And the hope would be, okay, so images of single digits, black and white, yeah, we were able to do that pretty well. But if you wanted to, like, recognize people's faces and distinguish people's faces, that network just didn't have the, the expressivity needed to do something like that. So you certainly wanted to be able to classify sets of images that were, bigger and more varied. It was widely understood you need to have more layers in your neural network. But that also means a lot more parameters, and that means that you better have a lot of labeled images to learn from to avoid just, overfitting. And that means that a lot of images, a lot of weights to tune. That means that you need to have good computing power. And it doesn't take long if you start scaling up the sizes of networks and the sizes of images and the number of images to, outgrow the gains that were made in computational speed in the 90s, which were significant. So let's see. So here was a challenge kind of laid out and done so painstakingly a decade ago. So I guess 2009. There was a big, somewhat crowdsourced project to label millions of images. And this created a database known as ImageNet. And it was agreed that this would kind of be the standard data set to use going forward to try to teach computers how to see. So millions of images with thousands of distinct labels. This structure here of going from this general mammal on the left down to husky on the right, that organization was important for the construction of this data set, but the data set ultimately is just these images on the right with specific labels like husky or trimaran below it. But again, so it was first released in 2009. There were 3 million images, 5,000 different classes, and quite specific. So not just recognizing a dog, but recognizing particular breeds of dog or particular types of trees and things like that. So that at least addressed one of the concerns with trying to build better computer vision was you need to have a whole bunch of images that are labeled, meaning that we already know, what we have to tell the computer how to learn by giving it some of these labels. And starting the next year, there was this annual challenge of how well can you do, training an algorithm on this data set to predict the correct labels on a held out test data set. The first year they did this in 2010. So I should say, again, I'm not trying to give an unbiased history. So most of the history of computer vision up to this point in time had nothing to do with deep learning or neural networks. And so actually all of these models that were used in 2010, none of them were convolutional neural networks. There were other techniques that, that we're just not going to talk about today. But here's a summary of the results for these models. So these were submitted by universities or other research groups. And if you ask the model to predict, basically take 5 guesses for each image of what the correct class is, the best model had an error rate of 28%. So, in some sense, that's still pretty impressive. That's about 2 out of 3 times more that it can pick the right image. And again, some of these images are pretty specific. But obviously, still a lot of room to go, and still not seeing as well as humans can see. And you can see some of these submissions did far worse, and only about 80% error rate. If you have to just take one guess, then the best model was about 50-50, guessing the right class. So that's to give you some context for how surprised people were in 2012. So in 2012, this paper was released on how to train deep convolutional neural networks So again, it's similar to the picture of the network we saw before, but with many more layers now. And this was able to, in the course of those 2 years, nearly cut that error rate in half. So the non-neural network models were still hovering around 26% error rate for the best, and this was 15% for that top 5 error rate. So it was really a night and day difference in terms of image classification. So this one used, so the picture we showed before had basically 2 convolutional layers and these other layers that helped it along. This one had 5. And so we're already talking about, 60 million or so weights. That's how many free parameters you have to tune to try to fit this function. And one of the big enablers of, optimizing this function with 60 million inputs was that people in the early 2000s figured out how to use graphical processing units, so GPUs, basically graphics cards inside your computer, to do some of this computing rather than the CPU. So if there are probably people here that know more about computing than me, but the GPU is responsible for graphics on your computer. So a lot of development was done for like video game graphics or movie graphics. And what they do really well is that they are like amazingly parallelized. So as opposed to computing things in sequence, much of the computation that has to be done for these graphic cards to render graphics is very parallelized. And as it turns out, the work that needs to be done to train one of these neural networks is, sending images forward through the network and then sending the errors and the gradients backwards. What it amounts to is just multiplying a bunch of really big matrices. And using GPUs, you could parallelize that process and basically do that really fast. So I mean, that's what was special about GPUs, is that they could multiply really big matrices really fast. And a model that might have taken a week to train could now be done in a couple hours maybe. And so that allowed them to choose more layers and more weights. So a natural question then is, can you keep going deeper? And people found that if you tried to go too deep, eventually the accuracy of your model would kind of level off and then eventually even start going down. And that seems counterintuitive, because if you have more layers, it just gives you more freedom to fit to your data. And so you might even think that, well, if I add layers, I should never be doing worse, at least on my training set, provided that I can learn an identity layer. So meaning if I can learn how to classify images with 5 layers, I should be fine with 6 if I'm smart enough to learn that I can just do it with 5 and then leave nothing changed through the last layer. And that was a key idea behind the next big advance, was basically carrying this identity along for the ride in your neural network. And so instead of asking it to learn this input to output mapping, you're asking it at each layer to learn this residual mapping. So instead of x being mapped to y, you're mapping x to x plus y prime. And what the weights try to learn is the y prime. And that means that you shouldn't have to worry about having too many layers, at least in theory. And in practice, this was just a few years later, 2015, that error rate got down to less than 5%. And actually using this residual network strategy. And that was actually the first time when the algorithm did better than the human labelers. So again, some of these labels are pretty specific, like breeds of dog, for instance. So no individual human classifies these perfectly. And this machine actually did a better job. Anthony, do you mind giving me a time check at this point? When should I be stopping? Soon?
Yeah, if you want to go for another few minutes, 5 minutes or so, and then we can end with some Q&A. Sure.
So here's a probably unintelligible picture of how you stack up these residual layers. All you should take away from this picture is that things get deeper. So you get more layers. And actually that award-winning model on the last slide used more than 100 convolutional layers. So I mean, you're talking about almost an order of magnitude increase from the original ones. So basically, what revolutionized things were this combination of three things: a lot of labeled data, better computing using GPUs, faster computing, and some of these techniques that allows you to go deeper without, and still have convergence of the training process. Here's a couple of slides that show you that this network is doing what people imagine it would do. So these are what some of the filters in the first layer look like for one of these ImageNet trained convolutional neural networks. So you can see they're doing things like detecting edges or pairs of edges or stripes or kind of these gradients in color. And you can see there's also, I mean, there's definitely some redundancy here, but not a whole lot. I mean, these filters are all kind of doing their own thing. If you look deeper down on one of these deep networks, you start to get some stranger looking pictures where you can see things like what looks like maybe texture is being, understood in these layers here. You could also ask one of these networks, so here's an image, you classified it as a dog. Why did you say dog? Which pixels were particularly relevant to that classification? And you can make these nice heat maps like these ones. And there's a couple different approaches to doing this, but you kind of have to, again, take some signal backwards from your classification through the network back to the input and see which pixels were really used here. And, we said this with the dog, and here's why. And on the right, we classified this as a cat, even though there's both a cat and a dog in the picture, but you can see it kind of did so for the right reasons. Okay, so maybe I'll skip. Well, let me just say one more thing. So what seems like it could be intimidating at this point is that we needed these millions of images and these like unrealistic compute capabilities to accomplish this. So now if I'm working at Ford and I want to say like, I want to put a camera in a manufacturing plant and say, when do these cars have defects in their paint jobs coming off the assembly line? I don't want to collect millions of images and label them and then like invest in millions of dollars in computers to do so. So thankfully for all of us, there's been a lot of success with what's called transfer learning, which is basically teaching a computer how to see generically, and that takes a lot of data and a lot of computing power, and then taking that model which has already learned how to see and just kind of tweaking part of it to accomplish a specific task. So now you can do things like like detect paint defects with a really small number of labeled examples, because you're starting with a model that already knows how to see, essentially. Okay, I have two more slides, and I'll probably just go through them too fast. There's still plenty of challenges that exist, although machines can classify images as well as or better than humans now. Here's one kind of like famously scary example. Here's an image which is classified as a panda. And here's a clever addition of noise to that image, which to our eyes doesn't change it at all, but to this particular model, change its classification to a very confident vote for gibbon, a completely different kind of animal. So this is kind of maybe a cute looking example, but there's less cute examples of like cars that can recognize stop signs, but you can put essentially a little QR code and tape it onto the stop sign, and then the car won't be able to recognize the stop sign anymore. So you can imagine how that might not end well. So there's still plenty of, and there's things that have been done to address this, but there's still plenty of challenges left there. There are also some issues that have been noticed of like with facial recognition. So let's say you wanted to use face recognition to, to do some security surveillance in public and say, oh, some crime was committed. Well, here's a person who was there who might be responsible. It turns out, and maybe for a couple of reasons, but a lot of these recognition algorithms that have been trained do a much better job detecting and classifying white faces than they do non-white faces. And so you can imagine how that's a serious issue. If you're going to use this as evidence or reason for suspecting someone, disparities in the model's success will naturally raise all sorts of questions about whether this can and should be trusted. And okay, I think I'll stop there. Actually, sorry for going a couple minutes over, but I want to leave some time for questions.